Hi, in this STR8CHEM video, we're going to look at what does it mean by the law of mass action, equilibrium law. Equilibrium law is basically explaining, it explains the relationship of the reactants and products at equilibrium. Okay, so basically the equilibrium law explains the relationship of the reactants and products at the equilibrium. It can be expressed in two forms. And what are those forms? Okay, the first one, it can be expressed in terms of concentration. And if we have that in terms of concentration, we're going to have the Kc. So that will be the equilibrium constant expression. And then we have in terms of pressure. So if you have in terms of pressure, that one will be your Kp. So Kc and Kp over here, this is what we call the equilibrium constant expression. Okay, so remember, when we talk about equilibrium law, when you try to explain the relationship between the reactants and products at equilibrium, we're going to refer to Kc if you want to have that in concentration, or Kp if you want to have that in terms of pressure. Now we're going to look at a few examples. So how do we write Kc and Kp? To write the equilibrium constant expression is very easy. But before we're going to go there, I just want to draw your attention to this reversible reactions that we have over here. Okay, in terms of reversible reactions, we have two types. And the type that we have over here is what we call, since we have gas, 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 these two reactants are in the same phase, which is gas. And then when you look at the products over here, it has the same phase as well. So what do we call this reversible reaction then? Since all of them has, the same phase, therefore this is what we called as homogeneous we have homogeneous equilibrium. Or homogeneous reactions, because they have the same phases. Right. Now, let's get back to our first question just now. How to write equilibrium constant expression for concentration Kc, equilibrium constant expression for pressure. For this, it's very easy. Now, let's start with Kc first. I'm going to write that in blue for Kc. So how do you write Kc? The way we're going to do this is we're going to put concentration of the product to the power of m over concentration of the reactants to the power of n. And how do we do that? Okay. So now, look at your reaction over here. This is your product, which is SO3, and it has 2 mole in front of it. Therefore, what you're going to write is here, concentration, we're going to use square brackets for concentration, SO3, and you're going to close that brackets. Remember, for concentration, it's going to be square brackets. And then look, right there, you have 2. Okay, you have 2 in front. So you're going to put to the power of 2. Right? And then, next, you're going to go over to the reactant side. So divide by concentration of your SO2, and then you're going to close that brackets. And here you have to the power of 2. Okay, to the power of 2, that one, times with the concentration of oxygen gas, concentration of O2 gas to the power of 1. So you don't have to write 1 over here. We know that it's going to be to the power of 1. So this is the Kc expression for this. Very easy, isn't it? Now, what about Kp? For Kp, I'm going to use green, perhaps. So for Kp, it's going to be exactly the same like what we have done just now, but instead of using square brackets, we're going to use P, because we're trying to write for the equilibrium constant for pressure. So you're going to write P over here, and SO3. Now you're going to put round brackets to the power of 2. Okay? Over pressure of SO2, remember, round brackets to the power of 2, and you're gonna times with pressure of oxygen gas, close that brackets to the power of 1. So when you look at the Kc and Kp, they look quite similar. But for pressure, we're going to use P, and then we're going to use round brackets. So do not mix that up. So square bracket is for your concentration, and this is how you're going to write for your pressure. Let's have a try at another example. Again, if you look at this reversible reaction, this is what we call as, that one is gas, that one is also a gas. Both of them are the same phases. Okay, so this reactions over here, we call it as homogeneous. Okay, so the Kc is, you have NO2 here, square brackets, NO2, close that bracket, and you have 2 in front of that. Okay, right there. So this number 2, you're going to write the power of 2. Divide by concentration of N2O4. Divide by concentration, square brackets, remember that, N2O4, you close that bracket, and now that one is to the power of 1, because for this reversible homogeneous reaction, we only have 1 mole of N2O4 decomposing to produce 2 mole of NO2 gas. Now, let's have a look at the Kp. Okay, equilibrium constant expression for pressure. So you have P for pressure and O2. Okay, for NO2 there. Round brackets to the power of 2 over pressure of N2O4. You close that brackets. So this is the Kp expression for this reversible homogeneous equilibrium. Let's try another one. So over here you have a lot more reactants and products, but they're also going to have the same principle when you want to write the Kc and Kp. Again, it's good for you to check, are they going to be homogeneous or heterogeneous? Later we're going to look at heterogeneous. So all of the reactants and products, they are at the same phases. So this is what we call as the homogeneous equilibrium or reaction. So again, Kc, we have CO square bracket for concentration. CO, you shut that bracket, and then to the power of 1 times with H2 concentration to the power of 3. Right there, 3. So this to the power of 3 is that number right there. Okay, so divide by the reactants that we have there. So CH4 concentration to the power of 1 times with the concentration of H2O to the power of 1. The Kc is this. What about the Kp? I think you can guess it by now. We're going to use round brackets, pressure CO, close that bracket, times with pressure of H2 gas to the power of 3 over concentration of PCH4 times with pressure of H2O, and you shut that brackets. So that's how you're going to write the Kc and Kp expression for that reversible reaction. Now, a very, very important tips for pure liquid and pure solids. The concentration are not going to be included in your Kc and Kp. Okay, they are not included in the Kc nor Kc and Kp. Okay, so when we write Kc and Kp, when you have pure liquids and pure solids in your equilibrium reactions, we're not going to be taking that into consideration. Why? The reason is because pure liquids and solids are constant. Okay, they are always going to be constant. So that is the only thing you need to know about pure liquids and pure solids. To explain about why they are constant, it's going to be another discussion, and that's going to take a long time. For now, it's enough for you to know the reason why they are not considered in the Kc and Kp is because they are constant for pure liquids and pure solids. If you noticed, over here you have all gas. You do not have liquids, you do not have solids. Okay? So now let's have a look at this example. Okay, so we have solid phase over there, gas, and this one is gas. They are not the same, okay? You have solid and gas, therefore this is what we call as heterogeneous. I'm going to write that properly. Okay, heterogeneous equilibrium, because it is a mixture of solids and gas inside the system. So how do you write the Kc and Kp for this? Okay, since we have talked about just now solid, pure solid is not going to be included in the Kc and Kp expression because it is going to be stay constant the whole time. So how do we write the Kc? So again, we're going to start with the product first on the top. Concentration of NH3 to the power of 1, because you have only 1 mole of NH3 being produced, and then 1 mole of HCl. Concentration of HCl. Okay, so since this is constant, the value of that constant will be divided by 1. Okay, because down here, this is 1. The value of solid is 1 because it is constant. So you're going to divide by 1. So when you have concentration of NH3 multiplied by the concentration of HCl to the power of 1 for both, divide by 1, you will have Kc equals to NH3. So that is how you're going to write it. Okay, so it's going to be the same as for the Kp. So Kp now will be pressure NH3 times with pressure of HCl to the power of 1 for both. And you do not have the pressure for your solids and concentration for your solids over here. Okay, let's try another one over here. We have gas, liquid, and gas. So this is heterogeneous equilibrium. So how do you write this? Okay, so the equilibrium constant expression concentration for this heterogeneous equilibrium would be concentration of this HBr to the power of 2 divided by concentration of H2 over here. Okay, and this is not going to be included for Br2 liquid simply because it is a pure liquid. Okay, but if you have aqueous over here, you can put that into the Kc expression, but pure liquid is not going to be included. So that is the Kc expression for this heterogeneous equilibrium. Let's have a look at the Kp. I think you should be able to guess. How does it look like? So you have pressure Hb Br to the power of 2 over pressure H2. Just like that. It's very simple, very easy. Okay. Now, what about this? We have a aqueous phase, solid, aqueous, and solid. They are not the same. We have pure solid, and now you have aqueous. So again, this is your heterogeneous equilibrium. So how do you write the Kc? So we're going to try to write the Kc first. Now, over here, you have solid and you have aqueous. Obviously, solid will not going to be included in the Kc expression because pure solids and pure liquid, they are constant. So we're going to take only this aqueous. Okay, aqueous and pressure can be included in your equilibrium constant expression. So it's still going to be the same. Concentration, you have I minus. And when you look in front of your I minus, you have number 1 there. So you have 1 mole of I minus being produced by this equilibrium reaction. So you have to the power of 1. So when you go over that side, you have to divide because now this is the reactant side. Okay, this is your solid, so it will not gonna be included. Remember that. We're only gonna take into account this. So the concentration of Ag, Cn2 minus, and you're gonna close that square brackets because your aqueous reactant over here is 1 mole. You have to the power of 1 there. Now, what about Kp? What about Kp? So in the case of aqueous, we do not have Kp for aqueous. Okay, because you only have aqueous over here, you have aqueous over there. You do not involving any gas, no gas. So you do not have to write your Kp. There is no Kp expression for this because it has aqueous. Okay, you do not have gas, and right here, right there, they are solid. Okay? So some good tips you need to remember. Always remember that for gases, you can have, it will be in the Kc, and it will have Kp as well. But for aqueous, you only gonna involve that in Kc. You do not have that in pressure. Remember, when you learn about ideal gas, PV equals to nRT, only gas that we're gonna consider the pressure. Okay? So we don't take the pressure of the aqueous reactant nor the aqueous products. That is a very good tip.